Hi, my name is Art Lichtenberger. I'm a professor at UVA, and I'd like to talk to you a little bit about research and research opportunities at the University of Virginia in my group. I collaborate a lot with Bobby Weichel, Scott Barker, Mike Siberry, and I'm director of a microfabrication clean room at UVA, which is spanking newly renovated and expanded. Very exciting. And I'm just going to give you a little piece of the work that my group, and often in collaboration with those folks, undertake, and maybe it's of interest to you. Let's see if I can. Here we go. So I'm a professor at UVA. $25 million, it's more like $30 million now. Renovations of innovations and fabrication IFAB facility, with emphasis on multifunctional microfabrication and scalable biomanufacturing. I'm particularly interested in superconducting and millimeter and submillimeter materials, devices, and circuits. And as I mentioned earlier, I collaborate a lot with Mike Siberry, Bobby Weichel, and Scott Barker. And I'm also very involved in the Applied Superconductivity Conference. And if you join up with us, good chance you'll, COVID willing, he'll be going to Honolulu, a shameless plug for my conference in 2022. I'll be the president of the conference and the program head. All right, so my playground at UVA is experimental in most part. At the top row, you see equipment, the fabrication equipment, whether it be a scanning electron microscope, deposition tools that we've constructed ourselves or purchased, a view into the newly renovated clean room. So we're think and tell, though we're not using cassettes. We hold our wafers with tweezers, one by one, process them. Maybe a couple in the flow, but there's no machines running them. You're pushing buttons, you're understanding how these tools work, from material science side of it, grain size, grain boundaries, film stress, morphology, to actually microfabrication techniques to create circuits and then test them. And so the second row has some pictures of devices we've made. This third over is a picture of a 5-micron thick silicon chip with gold beam leads sticking out and superconducting circuits on it. So it's a fun world to play in. These are $100,000 million sort of tools, which is fun in its own right. Though the emphasis of a lot of my work is superconducting, the things you'll learn will be applicable to semiconductor work as well. And then the end result are things that go and do things, right? So we're not just making widgets, we're making engineering new circuits and so forth to accomplish some more science. So on the left are 2 wafer probes, which use split block technology that we're very familiar with in our work in astronomy and other millimeter submillimeter waves. And we've taken our ability to microfab chips, and we've turned it all on its head, and we realized the first terahertz probing capability. So a wafer probe, we want to go in and make microwave S parameter measurements. We're part of the first terahertz transistor project with Northrop Grumman, and we make a chip that gets held between these 2 waveguide blocks. The chip itself is the probe, which is kind of neat. So it's not wires, it's not pieces that we've hand assembled. It's all on a chip, and the chip is thin silicon, which is has very convenient properties for this application, where we're landing the silicon chip, which is sticking out between these metal blocks, and it's touching down, skating, and the circuitry on it is matched, and away we go. 2 devices that go as mixers, superconducting mixers for radio astronomy. National Radio Astronomy Observatory is headquartered in Charlottesville. We have a long-standing research collaboration with them and funding to help them realize state-of-the-art instruments, look up at the sky and speak to where we are in the universe. Another playground. I'm an experimentalist at home. I love to cook. big dogs. My wife Liz and our kids are pretty much grown up, off on their own, but we enjoy having family. We enjoy long dinners and conversation, and of course cooking. So what really excites me about the work at UVA, and I think this is true for all of my colleagues in our department. It's a great bunch of folks, and we love working with students and colleagues, right, and grappling with the sometimes striking scales of the universe, the very small, the very big. In my application in radio astronomy, we're grappling in some ways in the humongous, right? So distances out to black holes and so forth, the whole scale of the universe. It's fun being a part of that. I'm not an astronomer, but to interact with astronomers, to create instruments, to working with them to do that, and knowing that what we're making is going on and having impact on that scale. Love being a scientific detective. So right. So you're making the jolt of discovery and making connections, and the beauty that abides everywhere in the universe. I still take a wafer out of a sputtering system that has a gold coating on it, and mirror smooth, glistens, and it's, I still find it beautiful, very, very fulfilling. So there's a critical impact of superconductivity on science, and it's really breathtaking in scope. And I've been pushing this at the conference level, right? In realizing that we're having a significant impact on society. My particular area is radio astronomy, black holes, pulsars, stellar, galactic evolution, gravity waves, possible life in the university, to super colliders, to quantum information, to health. And talk in particular about radio astronomy. Jansky, in the early 1900s, realized that there was a place for radio astronomy at the astronomy table, and it's sort of adding to the arsenal of how you look at what's beyond us, beyond our Earth. And so imagine having a 5-course meal. You want to be able to use all your senses in it, and radio astronomy brings a additional sense of that. And so Robert, Penzias, and Wilson, really got it going. Nobel Prize winners, of course, and they realized the universe wasn't just made up of stars, which up to then, most of the observing had been, let's look at those stars. But there's chemical signatures, there's gases out there which are fundamental to understanding the universe. And if we could get, and with radio astronomy you can, and other techniques now, you can look at those chemical signatures and map out how much gas is there, how hot it is, and how fast it's moving. And in fact, space is just jam-packed with a soup of electrons and molecules that we can look at. For example, ALMA, which is an international consortium of countries working together to build a multi-billion-dollar instrument in Atacama, Chile. And this is using a band 6, which is a mixer device we fabricated at UVA, looking at the Orion Nebula. And so the backdrop view is with Hubble, and the inset is using our detectors to look at what is actually there for signatures of wavelength. And this is an organic molecule, ethyl cyanide. So realizing that there's the soup that perhaps life could come from, organic materials, it's out there. So that previously was not known. It's been, many of the discoveries of molecules in space have been done with devices from our laboratory by scientists before me, and now my group. So the ability to use radio astronomy to match chemical measurements in the lab, you can see what the signatures and find them in space, helps us understand the chemistry of the universe. We're particularly interested in millimeter and submillimeter wavelengths. So with Bobby, Scott, and Mike, we have a very strong effort in this area. And to understand this a little bit better, just consider classical electronics. So you have voltages and currents. The devices, the scale of the devices is much smaller than the wavelength. So we're talking low frequencies. Electron inertia is negligible, and electrons are doing the work. This is the land of capacitors and resistors and transistors. We live, though, our group, more in the millimeter, submillimeter wavelength, where you have waveforms, where the device size is on order of the wavelength, where the photon energy is on order of the thermal energy. You have to consider electrons and photons, and you have waveguides and mirrors. And then you have quantum and quantum optics, where Joe Campbell and Andreas Belling do excellent work here at UVA, use this IFAP facility. You have energy transition in photons. You have lengths now larger than wavelengths, the scale of the device larger than wavelengths. Electrons are way too slow. Photons are doing the work, and this is the land of lasers and photodiodes. And there's overlap between these various regimes, but this is what it is. And we love living here, where it's you're working both electrons and photons. So heterodyne radio astronomy receiver, which is where a lot of the devices we make end up. We do what other superconducting work than just mixers, but this is a great emphasis of us. You have the telescope dish. So here's a picture from Atacama, Chile, with some of the 64 telescopes that live up there. You have a horn, so collecting it after the dish goes into your mixer. There's a local oscillator, a very singular frequency. You have tuning and bias, DC tuning, and the output is the mixture of the harmonics of the signal and the LO, which is a singular frequency. And you've downshifted down to an IF, to a lower frequency. And you have a very high-end amplifier. NRAO has a strong program in that this area, and it's amplified, and it goes on to filters and other amplifiers. So in concept, you have your LO frequency, you have your signature from outer space, or could be in the lab, and you beat them together, and you're looking to get out the difference frequency. And so heterodyne mixing shifts that are a signal down, and without the loss of the phase and the information on it. It's not just a power measurement, and that's what the heterodyne comes in. It's very important. And you can understand this, if you have any, if you played a musical instrument or near a piano, play two notes next to each other, and you'll hear the sloshing back, and that sort of wavering back and forth is that different frequency. And you can do this mathematically. You can multiply two cosines, just go do the math, and there's a difference term, and that's the term we want to optimize and maximize. That's the signal that we're trying to then amplify and put into filter banks and gain information on. So UVA and radio astronomy, there's a rich history in this. Bob Mattow, UVA, and Sandy Weinreb at NRAO, the director of NRAO at the time. In the 1970s, they developed state-of-the-art gallium arsenide semiconductor Schottky mixer diodes. So they realized that the best detector at the time would be a semiconductor detector, and it was simple in concept. There's a very finely pointed wire, this is on the order of a couple of microns, and devices all over. It's a metal semiconductor separated by an insulating honeycomb, and you put the tip down, and it would hit and slide in, and you'd be in contact, and you would have made a device. Not integrated, hard to put series of these together, but this was the state of the art for many years, and radio astronomers would come and pilgrimage and come to our laboratory and work with Bob with new designs, and we'd go ahead and figure out how to realize those designs, and off to radio astronomy observatories they went, and really opened up the field of radio astronomy. By 1980, UVA was internationally known for this capability, and this is about when I joined the facility as a graduate student. In fact, we also do scale radar systems, another very strong emphasis. That's with the National Ground Intelligence Center, and Tom Crow followed Bob as being the director of the laboratory, and really pushed that collaboration, which exists still to this day, where in concept you'd rather not have to test out whole full-size tanks or what have you. If you can make a model that's much smaller, easier to manipulate and cheaper to make, but test it at a higher frequency, it has the same cross-sectional radar area and all. And so if you can do these experiments at higher frequencies, you can save a lot of money at the other side. So we have a strong program in scaled radar systems at UVA as well. Tom left UVA quite a few years ago and formed a company, Virginia Diodes, which is now internationally known in around the world as a supplier and innovator in millimeter and sub-millimeter wave hardware and technology. It has, I think, close to 100 employees now in Charlottesville. It has its own clean room, and it's really a remarkable spin-off success story for our lab and for Tom. UVA and VDI devices have launched into space on dozens of radio astronomy and atmospheric studies and weather monitoring missions. Just listing a handful of them here, and that's very exciting to be up in space and having furthered science and the understanding of our universe. Just going to highlight two. One is the original ozone hole discovery was mapped with UVA detectors from our laboratory. Also in the early 1990s, the Upper Atmosphere Research Satellite, UARS, space mission, furthered that study of water vapor and ozone, and was very exciting. A lot of this work was done, ozone work initially was done with balloons. We're involved in the ALMA project. I mentioned it earlier, Atacama Array, and NREO is front and center in that work, along with a number of other institutions and countries. It's the largest land-based astronomical facility and endeavor by far in the world, and it's very exciting for UVA, from my perspective, to be part of that. You can combine individual antennas to be not just the sum of their individual areas, but by spacing them correctly and correlating the signals, the timing of them, and the information together with correlators, requiring precision timing and clocks. You can have a resolution that is an aperture of the spacing between the telescopes. So you can do amazing things with interferometry with arrays like this. Event Horizon Telescope. So most of the detectors with the EHT telescope that did the first imaging of a black hole recently were made in our laboratory, the superconducting detectors from Bobby and my group. It's very exciting. So, you use the Atacama Observatory and a number of other observatories, South Pole, etc., most of which use our detectors. And Shep Dolman is the EHT founder of that. Just, a remarkable discovery, the challenges of encountered and all that. I, in fact, gave a plenary talk at the Applied Superconductivity Conference recently, Superconducting Journey to a Black Hole and Beyond. And if you want to watch it, it's on YouTube. You can just put in Lichtenberger black hole, you'll probably find it, but here's the link for it. And I had a lot of fun with that talk. So, why superconducting detectors? Well, just very briefly, superconductivity, it's kind of neat, right? It has a transition temperature below which there's no DC resistance. There's a critical current density. You can only put so much current through it before it turns back into a normal material. And Bardeen, Cooper, Schreifer developed the BCS theory, which realized that electron phonon, so sound waves, basically thermal waves coupled with electrons, condensed all of those interacting electrons into Cooper pairs, all in one state, and with that comes an energy gap, and it's energy gap and the DC resistance in particular, which we take advantage of. So if you imagine two superconductors separated by an insulator, and I'm showing energy band diagram at 4 degrees Kelvin, so most of the states below the energy gap are filled, and most of the states above are empty. And this is it's an energy density of states diagram. So it shows you where states are and how they are filled. So these are filled and these are empty. And you can imagine if you bias one side versus the other, you're going to get this very large filled state across in this very empty set of states, and you have a rush of current. And here indeed are some of our electrical characteristics, hundreds of microamps versus millivolts. So that's millivolts. That you might be familiar with semiconductor and we'd be talking volts. So we're talking 3 orders of magnitude smaller voltage scale. The nonlinearity is abrupt. It's one of the most abrupt nonlinearities of nature. So this is the IV curve, this ideal switch that we're going to take advantage of in making detectors. And a section through a graphic of a single device would have one superconductor, the insulating layer, the other superconductor, and the area is defined by the SiO2, and then a wiring layer. So this wiring layer may go off to another device. So this is very easily integrated into having multiple junctions and more elaborate circuitry. And to get a sense of this again, to belabor the point, but a Schottky diode has a volt turn on. So the conductance, the IV curve, it varies slowly on the voltage scale of photons that we're considering, millimeter, submillimeter. But the SIS junction, it's not an energy detector, it's a photon detector. So 3 millivolts energy gap scale, hundreds of microns of current. The conductance here, right here, it varies very significantly on the photon scale of the frequencies we're interested. So that it makes it a different kind of detector. And in fact, you can, if you're just biasing a DC and you're shining RF on it, photon steps will happen. And that occurs because, I can go back, because maybe you've biased it so that your filled density of states is over here. The photon energy, it absorbs and it's given enough energy to tunnel across. So just the fact of shining RF on it will give you current, and maybe you have 2 photons absorbed. So it's really neat. This is a DC IV curve, and just by shining radiation on it, the DC IV curve is affected. And one of the outcomes of this, after Tucker and Feldman developed the theory of, well, how would these work as mixers, is that you can have signal gain. 2-terminal device, you can have gain. You're not creating energy. This is just at the frequency of interest, so it's still an energy loss, but you can get gain at where you're trying to mix. So these can be not only the lowest sensitive, but the highest sensitivity detectors, but ultra low noise, because you're minimizing the loss, and the following amplifier is going to add very little loss to the whole circuit. Potentially very wide RF and IF bandwidth, so they're really fun to play with. And the beauty of eventually of the approach that we've taken, other people have taken, is we've used the Gurvich trilayer, the group from Bell Labs, where instead of making individual SAS material, the whole wafer, you deposit niobium, you deposit aluminum, you oxidize some of it, you put niobium top, you have your SIS, one big junction across the whole wafer, and you're left to separate smaller patterns of it and make junctions on those patterns. So you're in a very clean environment. There's no resist. It's just you're making your SAS trilayer in the first step, and then you're processing. So here's SIS. Here's a cross section of a junction that's been made where you can see the black here is the SiO2. This is a focused ion beam cross section. Then we image this is the barrier layer, and there are the 2 superconducting layers, and then we have a wiring layer coming across. And so in looking at the top view, you'd have 1, 2, 3, 4 junctions. You have other circuitry and so forth. And then on the chip level, if this happens to be a soy chip with 5 micron or 3 micron thick silicon with gold beam leads, it goes into a split block where the radiation is guided inside the waveguide. Again, I'm telling you, we're sort of in between electrons and photons, both worlds. You need this technology, and that goes into a receiver, and you might have many receivers inside of a cartridge, depending on what they want to observe. They'll dial in one receiver or the other, and ultimately into a radio astronomy dish. So what's next? So what's in it for you? All right. So the world of microfabrication, I find to be, after 30 years, to still be exciting and really fun to work in. So here I am as a graduate student, and here is working on our first tri-layer system. And here we are with our newest tri-layer system, which a succession of graduate students, Rick Amos, Tom Cecil, Mike Sibery, and Jan Zhang as a research scientist in the background, helping foster that work and oversee continuity. We're increasing the technology of it and the sophistication and what we can grow, the different kinds of tri-layers. We have tools for etching, tools for depositing. We make chips. It's a fun little world. My wife's an architect, and in her world and in our world, you can add, you can take, you can modify. In our world, we're using $100,000 million tools. You put the drywall up. In my wife's world, and you wonder, you can take it down. You can, step after step. In our world, you're covering up. You can't go back. We don't have cassettes for statistics. So it's a bit of sleuthing going on, and it's fun, but it's very experimental, and that might excite you. What excites me, and if you go into this world, will excite you, is that there's been recent strong UVA and C's investments in the 17,500 square foot IFAB facility, and it increased by about 40% in size, and new equipment and beautiful facilities. $3 million was for advanced biomanufacturing. This facility now has a bio soft materials component to it, which is very exciting. $10 million for the microfab renovation itself. An additional, not $9 million microfab renovation, $10 million. I was the PI, but collaborating with many of my brilliant colleagues, we obtained $10 million from the university for new equipment for this laboratory, for the nanoscale material facility, and Bobby Weichel's far infrared terrace laboratory. And then UVA came up, engineering decided to invest an additional $6+ million to add the nanobio capability and to really give us a jump start going forward now that we're about to open up. And so it's a very exciting place to be, whether you're in my group or Bobby or Scott's or Andreas's or Chu's. A lot of good faculty doing exciting work in this lab. So you should check us all out. So what was my playground is your playground. It's experimental, from material science to chemistry to hands-on operating of equipment, and understanding what those equipments can do. People have ideas of what they'd like to have built. Can we build it? Can we figure out how to make chips that do the next thing? We're working on second generation ALMA superconductors with NRAO. Very exciting work. We were responsible for band 3 and band 6. These are the first generation results. We've demonstrated working mixers also for band 7 and band 8 that meet the ALMA specs. We are involved in the infancy now. We don't have funding, but it's looking promising. It's be a multi-year effort to eventually get the full amount of funding. But it's orbiting an astronomical satellite for investigating stellar systems, OASIS. It's spearheaded by Chris Walker, whom I've collaborated with on and off for many years. We go way back in developing new technologies, and this is a very exciting one where they've realized how they can dramatically increase the collecting area of a dish in outer space, and we've been asked to be part of this team to realize the SIS detectors for it, and so along with ASU, SRON, VDI, Virginia Diodes again, local in Charlottesville, Northrop Grumman, and other folks. We're talking next generation Event Horizon Telescope. You liked an image of a black hole? Well, how about a black hole movie? So that's the goal. They need more detectors. They need different frequencies, more telescopes. So all very exciting. So want to thank you for your time. I love the work I do, and I encourage you to check out many faculty who are involved in the clean room. In microfab, there's just lots of different opportunities, and if you like the experimental side of things and using your hands and from design to measurement, there might be a place for you here. So thanks again. Oh shit. Shit. I don't think I pressed recording. It didn't come up.
Oh my god.
Oh my fucking god. I can't believe that. Oh my fucking god.
No longer than 2 minutes.
Oh my god.
Sorry, I'm laughing.
Oh my god.
Sorry.
Oh my fucking god.
That's why you need a pro.